C6H4, CH, double bond N, C6H4N, double bond CH. I think that will be it. What was it my secretary told me to remember to look at? I know there's beauty and poetry throughout the campus of Notre Dame. I miss much of the poetry. Magnolias, that's what I was supposed to see. Sometimes I miss the poetry of the visible world when I'm thinking of another kind of poetry. When I'm thinking about molecules and atoms, I'm in the invisible world. It has its poetry too. You can't explore it without feeling awe and wonder. That's the root of all poetry, awe and wonder. By the way, this sign will introduce me. I'm Frank DeLalio, research professor in chemistry at the University of Notre Dame. The research I'm doing now has to do with polymers. Mer means part, so polymers means many parts. Polymers are synthesized from simple molecules called monomers. They are the giants among the molecules. I'll show you some of these polymers. This is a special type of impact nylon. How tough and ductile it is. Here is another type of polymer, crystal clear polystyrene. It is very stiff and shatters when bent. This polymer is a synthetic polyurethane rubber. Its elasticity is phenomenal. Paper clips can help explain how polymers are structured. Each clip represents a unit, that is a monomer. We can hook monomers on and on until we have many, many mers, polymers. We can hook on and on until the length is thousands of times the dimension of the thickness. This linear aspect is elongatedness. This great ratio of length to thickness is a characteristic of all polymer structures, just as in this chain in which each link is a mer. These links, pardon me, I mean mers, are hooked together with single bonds. They are strong. But if they're hooked together with double bonds, they are, of course, even stronger. Here is a chain in which the mers are hooked together as conjugated double bonds. The wonderful thing about double-bonded mers, unlike single-bonded mers in polymers, is that they will allow electrons to roam up and down the polymer backbone. This racing motion of the electrons back and forth causes a polarization in the chain. This phenomenon makes the polymers behave as if they were electrical magnets. Because they behave like magnets, they exhibit intermolecular cohesion. This intermolecular cohesion causes one row of paper clips, I mean mers, to adhere to another row. This intermolecular cohesion, caused by the electrons racing up and down, makes for extra strong material. It is strong because if a break occurs at a mer, the fragment cannot fly off. It is held there by this intermolecular cohesion. Here's an atomic model. It looks more professional than paper clips or chains. I'll use it to explain in another way what polymers are. Polymers are made up of atomic elements, usually carbon and hydrogen with nitrogen and oxygen, and in some cases with other elements. So here I take some of these elements and form an amino acid. Then I'll combine these monomers to form a polypeptide polymer. This is one of the most interesting because it is found in you, in your muscle, skin, hair, and flesh. There's a lot of you right here. The more we know about polymers, the more useful things can be made of them. For example, here in this office, there are useful objects made of polymers. This desktop, the tape in this recorder, the telephone, the frame in my glasses, this ballpoint pen. Even ordinary paper. NASA is exploring outer space, and its equipment takes a severe beating from heat, cold, pressure, and radiation. Polymers furnish them with materials with which to make equipment stronger, tougher, and lighter. We must continue to explore the inner world of the molecule so that we may increase the exploration of the outer world of the planets. The Greek philosopher Democritus said, "To understand the very large, you must first understand the very small." Here is where my staff and I do our exploring. Here we try to find the right monomers which will do the job we want. We must have the right MERS in the polymers to get toughness, radiation resistance, and thermal stability. These are the properties that NASA needs, and so does the rest of the industrial world. To get high heat resistance, we have to make polymers with uninterrupted double bonds. The scientist calls these conjugated double bonds. We'll take monomers A and B from their bottles and react them according to this equation I'm writing and see if they will synthesize a MER which will link together into a polymer chain we are looking for, a strong chain. First, we have to weigh monomers A and B separately and accurately on this electronic balance. If we are successful in this reaction, these compounds will react together to form a strong chain, a strong polymer. Liquid nitrogen is used to cool the trap to condense volatile byproducts. At the start of the reaction, the mixture is almost colorless. We are going to subject this mixture of monomers to a condensation reaction at about 720 degrees Fahrenheit, hoping that a double bonded conjugated polymer might result. As time goes on, we should see a change in the color in the reaction product. The polymer has turned bright yellow. At intervals of several hours, its color will change from the light to the dark end of the spectrum, going to orange, then red, then brown, and finally black. The color is now black, and yet, and this is important to remember, at this stage of the reaction, it can still be remelted after cooling it. The synthesis is complete. The quartz reactor has cooled, and here is one form of the final polymer. Here is the polymer we made, and the monomers A and B with which we started. We do know that electrons in the monomers do not have substantial mobility. But if we have done our work well and condensed these monomers together so that extended conjugation exists in the polymer, the electrons in our new polymer will run freely. And the electron spin resonance spectrometer can measure it. A few granules of monomer A are placed carefully in the spectrometer. The proper dial adjustments are made. Now, watch the oscilloscope. Hardly a wiggle, so very few electrons are running freely. Now we will test our new product. If our synthesis was successful, the spectrometer will show the electrons running freely. bits of our black creation are placed in the spectrometer. Now see the scope. See those electrons peak? That means that we have compounded a material with very many uninterrupted conjugated double bonds. Remember the paper clips and the double bonded chains? We now have a strong material, but will it resist extreme heat? Here is a piece of the shattered polystyrene that we broke in my office. When placed in the crucible over a mica burner and heated to about 1400 degrees Fahrenheit, it melts and decomposes. No good for our purposes. When we subject a piece of our new polymer into the same heat, it doesn't change. But this is not a very scientific test. We can check its thermal stability accurately in a thermogravimetric analyzer. We'll put a sample of our polymer in the cell. This tiny sample will be tested to about 2000 degrees Fahrenheit. Watch the X-ray recorder for our evaluation. Hours later, the chart shows that this polymer withstood 2000 degrees Fahrenheit in nitrogen and 1000 degrees Fahrenheit in air. So the polymer is extremely strong and heat resistant. But can it be fabricated? Can it be molded into shape? And then, will it hold that shape against intense heat? It is no good to NASA if it cannot be shaped into the form it needs. And then it must maintain that form. To mold a polymer, it must be fusible. That is, it must be softened by heat, then molded under pressure to the desired shape. It must be so compounded that if it is reheated thereafter, it will not soften again. We have just proved that our black polymer is infusible, and you might think it is useless. Remember, back in its intermediate stages of reaction, it was soft enough to be molded. We will take some of our polymer at that stage and subject it to heat. This demonstrates to my students that it will be fusible in the mold. But even classes must not interrupt some of our experiments. The material in the mold will be heated to 1100 degrees Fahrenheit under thousands of pounds of pressure until it flows into the shape of the mold. We found that if we premixed the catalyst with the polymer, it would complete its reaction. Condensation is continuing inside the mold. In the presence of the catalyst, it flows under heat, assumes the form of the mold under pressure, and then hardens. We can even control the time necessary for it to harden by changing the amount and kinds of catalyst so that the hardening does not occur before the molded shape has been completed. What you saw done here is basically what industry must do on a large scale. Soften, mold, and have it harden so that extreme heat will not soften it again. This, too, is beautiful and was conceived in awe and wonder. Those of us in fundamental research create things in the laboratory. It is someone else's job to find an application for things we discover. Ours is the discovery, theirs is the application. Like the poet, the basic scientist needs inspiration and freedom to think and dream, the courage and spirit to dream of the awesome wonders of the future of science. Yet this is not enough. He must also work long and late. Some people think that a scientist must be devoid of emotion. No emotion shows in a research report, but emotion was a part of every step of the creative process. Any man who looks into the depths of a grain of sand can't help being filled with the poetic glory of it. The architecture of these campus buildings is a mere nothing compared with the molecular architecture of a grain of sand. To the scientist with vision, there is no common clay. Those of us who explore the hidden world know that every time we open one door, we will reveal 10 more doors. And behind each of these 10 doors are 10 more doors. And on, and on, and on. The world and the universe are not chaotic. They are highly ordered. It is the destiny of some of us to explore that order, the order of the master plan. Not even polymers are prosaic. They are full of poetry because anyone who looks into them with any vision must be filled with the wonder of it all. The hidden world, to those of us who explore it, is breathtaking. Just as breathtaking as the world of trees, Gothic towers, stars, the cosmos, and the ultimate. C14H6, N2S2, O4, no O5, or is it O2?